Hi, everyone. Thanks for coming. So it's my pleasure to introduce Sriram Krishnamoorthy from PNNL, Pacific Northwest National Lab. He's done amazing work on high-performance computing, parallel programming models, fault tolerance, and runtime optimizations. And so, I'm very excited to hear what he has to say. Thank you.
Thank you, Madan, for the invitation. I met him a couple of months back now at Dachstuhl, and he said, okay, we should talk, right? And that's why I'm here and see if there's anything interesting that we can do together, with everyone working here. I want to do two things. I want to give a broad perspective of the type of research that we do, and then I want to dive into a few specific verticals. And depending upon what everyone's interest is, we could go more into one versus the other or just focus on the broad themes, right? So overall, in the lab, so Pacific Northwest National Lab is about 200 miles southeast of here. We say this is in the non-green part of the evergreen state. We are the rain shadow area, and the only thing green you see is either sagebrush when it's raining, otherwise it's not, tumbleweed is not green throughout the year, right? Or vineyards. Now it's just the hills are all covered with vineyards, and we have several, probably 100 square miles or something of vineyards around our area. It's just wine country now. It's a Department of Energy lab, specifically under Office of Science, which means that a lot of work that's done there focuses on science. And this lab itself prides itself in all types of chemistry that it does, right? And the computer science that happens within Office of Science is typically required or is typically done as an attachment to the fundamental sciences. So that's why if you see lots of the work that happens in computer science in the DOE labs would be related to high-performance computing, because high-performance computing is directly related to all of the simulations and calculations that they do. So I'll specifically focus on one aspect of high-performance computing work that happens in the lab, and this is related to compile time and runtime optimizations and transformations for high-performance computing applications. And the funding for this work, to give an acknowledgement, there are various forms of funding from Department of Energy, DARPA, IARPA, and lots of internal investment. And this is important because all the work we do in the end gets connected to some applications, and the applications are dictated by the funding agencies, right? So that's how it works. I'll talk about a few big themes. We do lots of work on various aspects of runtime optimization, focusing mostly on C, C++, Fortran programs, very little of, for example, Java or any of the managed runtimes. Work on compile time transformations and optimizations, again focusing on parallel codes in the sense of MPI and others. Various aspects of resilience. Here you could have a big machine where a node goes down and you want to recover from it, or you have a random bit flips happening on your machine and you want to detect or tolerate that. There has been some recent interest. It's amazing how the community moves, right? So far the goal has been, yeah, we'll get it working, and we anyway don't know beyond the 5th digit whether a result is correct. So there has been lots of focus on validation in the HPC and Office of Science community, but then correctness itself has not had a significant effort, right? Typically the DOE community has piggybacked on the mainstream community for all of these efforts. But now there is an increasing interest in saying that there are problems that are specific to Office of Science, scientific applications, and parallel codes that will not necessarily be solved by the standard tools out there. So we need effort on correctness, and we've started some work on that. I'll briefly mention some of the work that we've done to directly connect our work to applications. In terms of runtime systems, one, we develop and build various runtime systems. Global Arrays is 25 years old now. It's basically an abstraction for multi-dimensional arrays on distributed memory platforms. It's been used to build scientific applications, and it's more or less the de facto standard for computational chemistry. There is now an effort to pretty much completely rewrite the main computational chemistry code in the lab called NWChem. It's about 3 million lines of code. We're in the process, just started a year back. And there we are trying to develop an abstraction for many-body methods to do tensor algebra on them on distributed memory machines, and that's a big effort that we have going on right now. In addition to this, there is lots of research that happens at different stages, close to applications and then further out. So we've done lots of work on task parallel runtime systems, on shared memory and distributed memory machines. We tackle various problems. balancing load, managing data locality, automating different aspects. But the key aspect of all of this is that we want to automate as much of the problem of parallel programming as possible, but we want the user in the loop, right? So one thing application programmers hate more than anything else is us telling them what to do, right? So we want to develop essentially a framework where the user can come in and give us constraints on what they want to do or specify portions of the runtime execution, and then we take care of handling the rest. And as and when the users get more comfortable with what we have, they have confidence in what we do in terms of correctness and in terms of performance, if they believe what we do works, then they would hand off more to us, right? So that's sort of the framework for all of the research that we are doing here. We don't want to completely automate and hide abstractions. We want gray abstractions that allow for the internals to be exposed to the user. In terms of resilience, two big phases. You want to detect an error or identify how vulnerable your application is to an error, let's say a bit flip. And then once you identify it, you want to localize it. You want to only restore that portion, let's say from a checkpoint, and then you want to recover it. And this typically falls into, all of the work on detection falls into compile time analysis of your application, and then construction of detectors that exploit application properties. And at runtime, you treat the detector as telling you something has gone wrong and you want to recover from it. And this has lots of flavors in terms of correctness, approximate computing. Go ahead.
So how often do failures occur in your environment? I mean, in our HPC environments, failures are reasonably common on a small number of nodes. I would imagine that you do not have that problem, but I'd love to hear.
Yes, so it depends on the type of errors, and this is a conversation that's happening in the community, right? So traditionally, supercomputers, when they're built and the vendor contracts are written, they're written such that the mean time between failure of the machine is 7 days. So typically, you have your machine up for 7 days, you take it down over the weekend, test it, take away anything that's bad, and then you replace it. That's typically how vendor contracts are written. But the question that's being asked is, at what point is that too much, right? In one sense, you're building these custom chips, and if you see some of these chips, they'll have ECC in every aspect of it, and you pay for it, right? On the other hand, you have these cell phone processors, and everyone does ARM. It's much cheaper, and you more or less get the same flops if you want, right? Not commodity ARM, but just with a little more, you can do it. Then the question is, do you want to pay more and have a machine that runs all the time or as far as you want, or do you want to pay much less and have your application scope with it? And in fact, something interesting happened in terms of this data point, right? Everyone is using CPUs. GPUs came along the first time. They had no ECC, they had nothing. But then they gave you a 10x speed up in many cases that people were playing with. And every application team wanted to use it, right? So 10x speed up really is transformative, right? 2x, sure, but 10x is completely different. So they were willing to work around the errors in the system to exploit the additional performance. Now the question becomes, can we do it at the full scale? I don't know where we are going to end, because I don't think any vendor wants to end up on a New York Times or Washington Post saying that, hey, they built this machine for $100 million and it doesn't stay for 1 day. But as a user, we really want machines where give me the most resources possible and I'll take care of validating my code. Most often what you do is you don't have one answer, you have a distribution, and as long as the number of errors that affect the distribution is not much, your distribution is not affected as a whole and you don't care, right? So this is the difference between validating your result versus saying that every bit of your result is correct, and different communities fall in different points in the spectrum. And like I mentioned, we are starting some work on correctness. It builds off of our work on fault tolerance and compile time analysis, and it falls into 2 classes. And I'll briefly mention some of these. One is the notion of equivalence checking. Typically with faults, what we do is you want to have an idea of what you expect to happen. You have an idea of what's happening and you want to compare them, right? And some of the compile time analysis that we were developing ended up showing us how to check equivalence of 2 programs for special class of programs that are important in the HPC community, and that can now be used to check whether the compiler is producing correct code. The other one that we're starting to do when it happens pretty much everywhere is you can do static analysis to identify invariants, and typically we use these invariants to construct detectors, but it's no different from saying, well, this is an asset that your program has to satisfy at this point. Now you have correctness properties that you're enforcing, right? The interesting things where this differs from the commodity is when you have multi-threading and when you have MPI at a large scale, you have code that's not necessarily written in a managed way. You use Fortran or C and you have aliasing everywhere. Those details need to be handled. But the principles and crossover, there's plenty of things that we can learn.
Is the code, I mean, there's a lot of floating points, I imagine. It's not just integer arithmetic, right? You're doing...
I would say there are integer bound benchmarks or applications, but most of them would be heavy floating point, often double precision floating point.
So do you have abstractions that you guys have built that help you deal with floating point?
We are building some of them. So we do numerical analysis for certain kernels or program classes, and we can use that to estimate, for example, how many bits do you expect for different executions, and then that can be used to either build a correctness checker or it's a software detector for us.
So there are two different granularities of errors. So it's one, I think you're talking about bit flips in memory and transfers and so on. But there are other kinds of errors where the entire machine goes down. And all of these techniques will not handle the other, this like large granularity errors.
Yes.
Is that right?
Yes. So the interesting thing is we've, as a HPC community, had a lot more experience with things just going down. They've been happening forever, and we know how to handle them, right? So you do checkpoint restart, you identify these nodes are going down, you take them out of the machine, you recover on a different job, and so on, right? So the big issue is silent data corruption. You have a bit flip, you get a result, everything is fine in terms of the computation, but how do you know your result is correct? That's a new thing we've not dealt with, and typically this is a problem that has been studied in related community in embedded systems. And often what they do is run the same thing twice, you have approximations, redundancy in hardware because they can pay for it. And a satellite, sure, it's the smallest thing in the total budget, right? But then if you say 2x redundancy on HPC platform, typically they say $1 million per megawatt per year is the cost for just operating the machine, and we are in the 20 megawatt regime. Half the machine going away for just making sure result is correct is too expensive. So we try to find places where computer science intersects with applications. For example, if you say DOE, I would have said DOE, basic energy sciences, biology and environmental research. They care about their challenges, we care about doing computer science research, and we try to find these intersections where computer science techniques can be applied to solve parallel computing and scientific application problems, right? So this is an analogy someone gave at the Dark Stool where they're saying, we are trying to hammer all these things, but they're really screws, right? What you want to find are the nails among the screws that you can do with the hammer. You don't want to say, well, I can do this with computer science and I'm just going to solve every problem with it, right? We just have to realize that there are some things we cannot do. It's a community issue, it's societal, we just cannot change it. But we try to identify the challenges we can and address them. Now, this is like the broad perspective of what we do, and I'll give you some places where we have transitioned existing computer science research to solve HPC problems. So this is one thing that I mentioned about resilience and correctness, and often here what we do is we try to take existing tool chains. We are starting to play with tool chains that do symbolic analysis, but so far we've played with polyhedral analysis. This is basically you have a, let's say, a simple loop program or a loop specification of a more complex program, and then you can treat the operations that are done, the iteration points in your loop, the data accesses, all of these are integer sets. And there are lots of nice tools available for us to do analysis on these integer sets, right? Most often these tools are used to generate efficient code. You could be trying to generate code on a CPU versus GPU, you want to parallelize it, you want to have cache locality for various architectures and so on. We were among the first to use it from a different perspective in terms of resilience and correctness. So first thing we did was we looked at the problem of bit flips happening in the memory subsystem. So this is sort of motivated from the GPU example where let's say your memory does not have ECC. And it's not just the memory, it could be your memory, levels of cache, it could be a load store queue. Let's assume there could be a bit flip anywhere between a store and a load, right? And we were looking at efficient ways of detecting those errors. Then the next one is the problem of equivalence checking that I mentioned. Often the optimized code that you generate is going to be much more complex and often not have the same properties as the input program. For example, the input program could be a simple loop. The output program might be a recursive function, right? It could be something completely different. How do you check that the transform program is correct? And some recent work that we did is to look at simple affine loops, and as in programs that have a specification of a simple affine loop, and how they behave in the presence of a hierarchical set associative cache. Right? The typical approaches involve just tracing. We found that for these parts, which dominate many scientific applications, we can do closed form compile time modeling modulo sum assumptions. And then we have a big group in the lab on graph theory and combinatorial scientific computing, again HPC aspect of combinatorial algorithms. So we worked with them in this one instance to use graph matching and in one case graph coloring to identify how do you place your data. You have an arbitrary data structure and you want to distribute it such that you lose any one part, you can recover it based on the checksums that you place in the machine itself. And you're going to assume that now a given number, a bound is going to fail. You want to make sure that you are able to recover from the checksums that you have. Standard solutions have been provided for Cartesian distributions, assuming spare processes to store the checksums and so on. We came up with a general solution based on graph matching. And there are other things that I'll skip and we can come back to any of this later. So this is some recent work on essentially correctness / resilience, where we are doing forward numerical error analysis to identify bounds on what you expect your correct computation to be. And then the goal is that, let's say the user wants to guarantee that the result is correct to 4 digits of precision. Now, we try to come up with the minimal detection strategy in terms of placement and cost, as in space and cost, such that we are going to give that guarantee. And the interesting thing is, because this is a precise analysis, when we cannot, we can say that, we cannot guarantee this. Did you have a question? No? Now, this is all flavors of transition from core CS and numerical analysis to problems in the scientific computing domain. In the end, we want to transition as much of what we do directly into applications or into tools that then impact applications. So we've had a long history of collaboration with the computational chemistry community. In fact, the new rewrite that we are doing is more or less half chemists and half computer scientists, right? It's one big project. We've been doing some work on computational biology. There's lots of interest now in power grid, smart power grids, solar panels everywhere. Security also comes into the picture once you talk about power grids. And we transition our code to use scientific applications, and then there will be work on that just results in publications, and we just leave it there, right? And then expect the community to take off. So there is a spectrum of research that happens in terms of how it relates to applications. So NWChem is the chemistry code. So if DOE's chemistry lab is PNNL, NWChem is the chemistry code in PNNL, right? It does various forms of chemistry, ground state, excited state, various bases, and so on. NWChem has been used on pretty much every supercomputer platform in the world and has been scaled to the largest ones. And the current project, the goal is to get NWChem working or set up so that it runs the best possible on the exascale machine that's expected to be available around the 2021 timeframe. Now, I'll switch gears. So this is sort of an overview of different pieces. Now I'll jump into 2 verticals. One, I'll try to talk about in the next 15 minutes some work on polyhedral analysis, and then another 15-20 minutes on some of the runtime work that we've been doing. So this is, I've noted down, now this is joint work with folks in Ohio State, Indria, Colorado State. So first I'll mention correctness checking. We've talked about it a few times. You could take a trace of 2 programs and then check that they're equivalent, right? And the main problem here is that the trace sizes in some cases can be big. And often the challenge is that small problem size programs are not representative of the real thing. Because let's say you have a big application, you have a big cache, and so I'm going to use a tile size of 200 for my outer level cache and a tile size of 32 for my inner level cache. you really want a problem space that's big such that it's going to exercise all of these code paths. At that time, symbolic evaluation traces, these just start to become infeasible, right? So that's why you want to do something that's to the extent possible online. The state of the art to test all of these is that you initialize some values for the input program and the optimized program, run both and check the result. One, these are double precision floating point computations and you're checking for exact equality, right? That is one thing. And then you also have this issue that you're doing matrix multiply, for example, and you initialize everything to 0, your result could be correct, right? If on the output you don't do anything. So how do you initialize the inputs to guarantee that all errors are caught is a whole different open problem in itself, and we've not solved that. So we observed that in many cases, large sections of the computation are operating on affine loops. You'd be doing matrix multiply, LU decomposition, or any of these linear algebra computations, stencils. And the big thing now that I've heard going on and I'm seeing in the community is that the core kernels in machine learning happen to be affine loops, and the affine loop nest and polyhedral analysis community seems to be extremely involved in machine learning. We used to be asked, why is it relevant? And now it's the complete opposite, right? Everyone is being hired to go into industry and nobody can stay in academia anymore.
But though bit flips is the last thing they care about.
Yes. But then optimization through polyhedral analysis is exactly there. And there is an interesting thing that goes on, and there, I don't have it here, is that often you will have, for example, optimized kernels. Let's say matrix multiply, you have a kernel, right? But then the user writes a high-level affine loop nest. So the big question is, can you transform your program to take advantage of the optimized kernels you have? Or conversely, can you find sub-computations of your overall computation that you can map to the optimized kernels you have? And if you do it, you're going to have massive improvements in performance rather than anything that you can do directly through compile time, right? So here it becomes a variant of subgraph isomorphism. Well, the moment I say it, it's NP and bad things happen. But you could find portions of this because this is affine, and you can do equivalence checking to identify this. And this is a big problem, and it's mathematical. You can't just test a few inputs and say, hey, they are the same thing. And that's where there's lots of interest now, especially in the machine learning community. You have these optimized kernels, the user says something, how do you use them, right?
So in these applications, the control flow is very structured. I mean, it's very deterministic.
Yes.
Right.
And in fact, the data access patterns are independent of the control flow, right? So the control flow and the data access patterns are decoupled. So that makes it easy for you to do this analysis and do optimizations and transformations entirely at compile time. So there is nothing in there that's data dependent, right? The control flow is not data dependent.
Yeah, I was going to say that even runtime approaches like symbolic execution might be helpful here, because you just take one path and then if you symbolically analyze just that path, maybe it's okay.
Absolutely. I think this is where the two communities sort of meet. You can think about polyhedral analysis in some sense as symbolic analysis, except that you're talking about multidimensional spaces. That's really the difference, right? Otherwise, you're talking about symbolically identifying what a particular statement or a loop nest is doing, or what definitions reach a particular point, except now it's a polyhedron. So here are some examples, some that happen in real codes and some just made up, and all of these are equivalent, right? So let's just look at the left top one. So all I'm doing here is, it's a simple loop, 0 through n minus 1, and I'm copying into A the values in B. It's a simple memory copy operation. Now all these 6 are equivalent, right? So here, I'll go here for the B, right? All I'm doing here is I'm splitting the n, this loop, into chunks of size 32, and I'm copying 32 at a time. The reason, for example, I would do that is that this might be good in terms of cache locality. You might replace this with a single vector instruction that makes it much more efficient. Or you might have inner parallelism, a thread block on a GPU, and you want all of them to execute together, right? Various reasons why you'd want to write this way, then a compiler can take over and say, hey, I know what to do with it. Now, I'll jump from here to this one, only slightly different, right? I'm just, instead of 32, I'm just saying T, right? And then, well, for example, you don't know what machine you're compiling to. You just don't know the thread block size. You just put a T there. A T is a pragma. It's known when you compile the code, for example, as a pragma, or sometimes you don't. It's a parameter. And it's the exact same code as this. Here, it's one step further. Instead of doing it equally in terms of T, I'm just saying I have another array that tells me how to chunk it. I might do this because I know that the data is in a NUMA domain, it's irregularly distributed, and I'm just going to exploit that, right? This is a recursive function that basically implements the same thing by splitting it into different pieces. For example, Silk would do this. This is an example, it's a funny example that we just made up, where if you just know the parameters that you're using are coprime, you'll end up operating on each element exactly once. You're just randomly picking some distance off, you're filling it in, and then you just keep going, right? All of these are equivalent. Now, there are tools right now that can take two polyhedral programs, affine loops, and say whether they're equivalent statically. The only issue is only these two are affine programs. None of these are affine, right? So the moment you put a divide by t, that's not an affine program anymore. This is no way, this is data dependent now, right? Recursion, forget it, right? Unless you can translate the recursion into iteration, it doesn't work. And this one, I mean, no tools there can actually prove it, right?
For the C one to be equivalent, there are restrictions on T, right? T needs to be prime to N or whatnot.
Exactly. There are two things going on here. One, you could try to find out what are all the preconditions that need to be satisfied for these two to be equivalent. Or what we do here is that we just do an enhanced form of testing, which is that given some constraints or given some values, we can say whether these two are equivalent or not. So what we do is we actually run the program for the specific inputs, except instead of actually running with the values, we try to do this analysis. Effectively, we are now symbolically executing the program at runtime. Instead of values, we propagate what we expect to be at that point, and we check for equivalence, right? But the key observation for all of these is that in all of them, if you see they're doing A of something equals B of the same thing, right? So they're only moving these operations around. They're not changing the data layout. They're not changing how these things are accessed. So this is what we call iteration reordering transformations. And the thing about iteration reordering transformations is that you could do them in any order, but a particular operation is going to access a particular set of array elements, right, in the same form. Now the key here is that you could then look at the input program, which is a simple loop, and then a transform program, which could be much more complex, and then say, as long as I can find equivalences between statement instances in the source and the transform program, I can reason in the source space on what array elements it's accessing, check that those are the same array elements accessed in the transform space, and now I have a checker, right? And that's basically what we try to do. We try to look at the versions of array elements that are written, and then we try to make sure that the versions match in both the input and the transform program. In some sense, you can think about the key idea as you execute the transform program, but then while you execute it, you are simulating or symbolically executing the input program together with it. And that way, at any point, we know how much of the input program has executed so far, and then we check, is this a valid ordering of the statement instances in the input program? And then we can find if a statement instance is executed twice, if a statement instance is going to be skipped, all these things can be checked. And in fact, we can even say that as long as the checker keeps seeing operations, the algorithm is guaranteed to terminate, because at some point we'll run out of statements and we can say that you're executing too many.
This is definitely not true if we parallelize, right? Like the order changes. Definitely some of the transformations, the order does change.
So iteration reordering transformation says that you are reordering the iterations, but a particular iteration is going to write to the same locations.
Yes.
So that's the key property that we are going to exploit. So there are, for example, let me give you a transformation. You could take a stencil program, right, and you could have the total space, let's say in a 1D stencil, n times t, right? You could have you could have this being the space, right? Or you could actually have space that corresponds to just two wavefronts at any point. And you can show that given a program like this, you can transform it to only have 2n space. So this has n times t space, this has 2n space. And this is enough to compute a 1D stencil. Now, in this program, you're really changing the data layout and what each statement is accessing, right? There is a non-trivial transformation that goes on here to handle the dependencies and so on. But then, in our iteration reordering transformation, the data layout is exactly the same. If you look at any point in the program, from the perspective of the data elements, every data element is going to get the same number of updates in the original and the transform program, and the ith update to it is going to be from a statement that looks like this.
Okay. So it's an ith version of an array element. Right? It's not the ith update happening in the program.
Yeah, exactly. Exactly. Yeah. So that way you could change anything, but the write after write dependencies are preserved. Yeah. So now I'll quickly go over a few other things. How much time do I have? 2:35? 2:35? 2:45. Okay. So we were looking at cache modeling and simulation, and typically we have these large traces, and you would see HPC papers where there is lots of work on file systems and I/O architectures to handle traces, because sometimes they get to terabytes, right? We observed that in many cases, most of the computation is happening in simple dense loop, and scientific applications are designed that way because those are the kernels that can run well on a machine. So it's this tug of war where you try to design your application to run well on the machine, and of course you try to design your machine to run that application well, right? So there's a co-design that happens throughout scientific computing. So if you take a simple loop, this is a 2D loop nest, and you have Aij on the left hand side is updated from two different elements in A. Okay, we're going to assume that in terms of memory, you're going to load the values into registers, do the computation, and then write the result back. As far as the memory is concerned, the operations don't matter, right? You just read a bunch of values and write them. So this is now a program that's the memory view of the computation. Our goal is to see how does this program behave with respect to the memory in terms of accesses in the cache and the different parts of the memory subsystem and so on. So you want to know what are the reads and writes, for example, to a particular cache line. What is the working set at any point in your computation, right? How many elements do you access? What's the reuse distance that goes on? Or you might want to say that, well, I have this particular program or kernel embedded in a big application. Tell me what the state of my cache will be once I am done with this program, right? Another question you could ask is, let's say you want to think about vulnerability of your computation to a bit flip. Now you are affected by a bit flip only if you have useful values in a particular cache line. So we want to check if there is any dirty value or a value that's going to be read in a cache line at any particular point in time, right? So these are all questions that you can ask. Now that's a simple loop program. The only issues, and this is what was a challenge in the community, was that line size, for example, you take a particular address and then you don't access one element at a time in a cache. You access an element and the cache actually brings you an entire cache line, right? Now that is a parameter of the machine, and different machines will have different parameters. And another issue with these addressing is that given any multidimensional array, and multidimensional array elements are really nice because, well, they're polyhedra, right? Except that in reality you would linearize them based on the problem size, and then you get a particular address, and then that's what you use to do the access. So these things make the whole entire computation non-affine. Now what we did was, first we said, let's assume these are known, right? And now we are working on something else that I'll explain. We assume that these are known. Once you know these as constants, now you have an affine problem, right? And then once we have an affine problem, we solved a whole bunch of questions. So the state of the art in this work was 1991 and 2001. They had two different works, but then none of them could truly handle hierarchical set associative caches, various cache allocation and eviction policies, and we could do additional analysis. We don't just count the number of misses, we can exactly tell you what the misses are in terms of caches and when they happen, and that lets us stack one cache model on top of another. So you could have L1, L2, L3, and we could simulate all of them, right? Now part of this is figuring out the formalism itself, right, the formulation, and part of it is making it work. So in the end, we are dealing with a beast here, right? So polyhedral analysis is not polynomial. Some questions you ask, it could just take forever. So a big part of our work was trying to formulate it in such a way that with the tools available right now, we can get solutions in a reasonable time. Reasonable time as in minutes to maybe a few hours. You ask a slightly different question and it takes 12 hours and it doesn't terminate, right? So that was part of what we had to do here. But the key for all of this work was the assumption that we could identify the layout, right, and the line size as constants. Now one thing now we are doing, now that this whole machinery is available for us, is to
So a lot of these questions they call into an ILP solver in the backend.
So they don't necessarily use ILP. In the end, they ask this question about how many integer points are there in a polyhedron,
Okay.
and that question becomes NP. Yeah, it's, I think it's 2 to the 2 to the n or some big.
It's like, yeah, oh, that's the P sharp. Yeah.
Exactly. Yeah, it becomes extremely expensive. Yeah.
Oh, okay.
So are they, I mean, maybe tell us, are they custom, are you writing custom solvers? Or is it just you're using off-the-shelf tools?
We are using off-the-shelf tools, but then the tool that's off-the-shelf is being written custom by someone. So maybe the question that you're asking
for polyhedral solve, yeah.
Exactly. I guess the question you're asking is that community, right? Are the people that are writing the tools using existing tool chains? They're not, right? And that's a place where, in fact, we know that what they have are not the most efficient tools, but that's the most efficient out there. They know they are not the most efficient, but they believe we've worked so hard to get it to be correct to the extent we know. We're not going to try to muck with it, right? So that's an excellent question, and we could really use some expertise, right? And there is lots of work happening in terms of SMT solvers and ILP solvers and all that. This community has not yet exploited all of that expertise. Now I'll jump in the next 10 minutes. I'll talk about some work that we are doing on the runtime.
Explain how you handle the case. I mean, because you assume that the constants are known.
Yes.
But
So
in
the next
fact,
work that we are doing right now is that you really don't need to know which set a particular cache line address is going to fall into. All you need to know is if 2 different addresses fall into the same cache line. So what we do is that we'll say that, let's say the starting address of this array, or the starting address of, let's say you have a bunch of arrays and they have all these offsets, right? The first of them is going to fall into this particular cache set. Then you have everything else is related to that cache set. Then with that, you could basically say, related to that, I know it's going to fall into the kth cache set. And then I'll do the entire analysis. Now the key here is that that initial value for that is parametric, right? Now the formulation is actually non-affine. But we enumerate that k. But that k is usually bounded. The number of cache sets you have, there's no cache architecture out there with more than even 8-way or 16-way, right? We could go all the way up to 128 if you want, right? And then we have independent individual affine models for each of the values for the starting set, and then we can solve it. Yeah. So then that makes the problem bounded. So in all these cases, we are sort of working around the elephant in the room, right? That's really what we are doing. In the end, you need an affine formulation, and we come up with ways of making that happen. Now, if there are more things here, we could continue on the compile time part, right? We don't have to get into the runtime aspects. Go ahead.
I was just curious, the last point in your slide that you have an incremental calculation, is that just because LRU is such a simple policy, or did you?
Yes.
Okay.
Yes. So essentially, the basic idea is that something that's missing a k-way cache, right, will also be missing a k-1 way cache. You reduce the sets, number of things that can go into a set, right? Then it's still going to stay a miss.
So it's the number of misses that's the same, not the,
So
not the specific trace of misses.
So what we do is that we try to find number of distinct lines access the same set between 2 identical accesses, right? So let me draw the timeline. So let's say we have an access to array element A. Let's even call it cache line A, right? And then I'm going to have another access to the same cache line A here. Now the key question is, in a direct map cache, is there any access between these two, to something B such that set of A is equal to set of B, then this is a miss, right? Otherwise it's a hit. Now for a two-way set associative of cache, right? So then that's a direct map. Then if you add additional set, then the question becomes, do I have yet another distinct access such that all three are the same? So what we do is that we look at this interval symbolically, and then we keep subtracting unique instances to cache lines from this set. And then if the cardinality of the set is greater than k, then you know that in a k-way associative cache, this is going to be evicted. And that way we just keep subtracting, so it's an incremental algorithm.
So can you talk about the scale of programs that can handle analysis?
So with this one, there are two aspects to the scale. One is the problem size, the other is the complexity. So in terms of the problem size, we can handle really large problems, right? So you could put a matrix multiply with 1,000 or 10,000, it's fine. Exactly. Where it gets complicated is that if the code generated itself is going to become complex, this thing can quickly explode. So you could, for example, if you take a blast that's generated, for example, in Atlas or any optimized NKL or something like that, right? Those things run to hundreds of lines, lots of statements. Those become really expensive. So we've not been able to get those to work.
So maybe loop nests matter more, right?
Exactly.
And so how deep can you go? Like 4, 5 nested loops?
So there are two parts here. So one is, so in many cases you can replace if loop nest with if conditions and so on, right? Often it's not the nesting itself that matters. We can do 4, 5, even 6. It's how nastily they are set. So in the sense, if you think about it, for an exact solution, we are trying to symbolically evaluate the integer points, right? The moment you are not talking about integers, it's all easy. With integer points, it's always the corner cases in these polyhedra. So when you have different loop nests, one operating in this space and one operating in this space and another operating in this space, right? So you want to find out the subtractions of these. In general, you'll have exponential number of these fragments available, right?
Okay.
That's really where things go bad. So if you have a really big loop nest, A, B, C, D, E, fine. It's really when you do loop fusion and then index set splitting, and then you have all these fragments, you'll have a corner case with some of these if conditions can get big, right? You'll have like 10 lines of if conditions to say, if these conditions are satisfied, this point exists. Those become complicated. So to give you an idea, we've had cases where the polyhedral formulation of this can be tens of kilobytes, just if you just store it as the conditions, right? So it's not even, forget reading it, right? So it becomes big. And this is not even for the MKL like case.
How do these methods work in conjunction with unrolling? So if I decide to unroll my code, if certain parameters, can I still express it as an affine?
Yes,
program?
yes. So in the extreme case, it's a really bad case, but the extreme case, you could unroll the whole thing and it's effectively like an affine program, right? The only issue is now you fix the problem size. Yeah. If you can fully unroll it, you fix the problem size.
So then I start unrolling for
Yeah.
performance.
Exactly, yeah.
So you can still analyze as a polyhedra.
Exactly, yeah. And typical unrolling factors 2, 4, it should be fine. Yeah, even 8, right? It's really once you do fusion and index set splitting, the number of these loop nests or the conditions can become exponential, then bad things happen. Okay, I'll give a really brief overview of some work we are doing on runtimes. This is one specific vertical. We're doing various things. I'll just talk about some work that we did on tracing work stealing schedulers and then using that to improve its performance, right? So the basic idea is we have task parallel programs. Specifically, let's focus on recursive programs, right, that we are going to execute. And often these are parallelized using random work stealing. The basic idea is that we have a bunch of threads or processes. One or more of them have some initial work, and they all are let loose to execute, right? And they are asked to return back when the entire computation is done. Any thread is either working on some computation or it's idle. When it's idle, it potentially randomly picks someone else, a victim, and then tries to steal work from them, right? So together, they keep trying to do this, switch between idle and active phases until the work is complete. Right? So this started pretty much in the 90s. It sits on a robust theoretical foundation. It's shown to be asymptotically optimal. Several implementations exist. Now, one of the issues that we have from the HPC perspective is that random is fine often when you have a single NUMA node on one socket. You put it on a big NUMA node, things get expensive. And then you put into distributed memory machine, things get extremely expensive, right? Every communication that if you're accessing non-local data is expensive. And second, this is no memory, right? Many times we know that we are doing the same thing over and over again, or close to the same thing. You're doing a time evolving system or solving for convergence. You don't need to start over from scratch and say, I'll seed everything to process 0 and let the computation percolate, right? We don't want to do that. So we want to trace a particular computation. We say that, let's say the user is not responsible for load balancing the computation. But then we want the system to do something that the user would have done if they put in the effort, right? That's sort of the ultimate goal. So think about it as we have a non-parallel, it has concurrency specification, but non-parallelized computation that we want to analyze at runtime to come up with effectively a single program multiple data computation, like an MPI program, right? The user is not writing it, we're going to come up with it. That's sort of like the holy grail of what we are trying to do, right? This is not compile time, that's the key difference here. And there's lots of efforts there and roadblocks along the way. We are trying to do this at runtime, starting from a specific form of the program, right? So we say that we'll trace the computation and then we are going to use the trace to inform the scheduler what it can do. It cannot just do random stealing anymore. It's going to take the trace to do something with it. Now, I will probably skip all of the details about tracing. I'll just give a glimpse of what we are doing and we can talk in more detail. So to show you roughly what the sizes of these traces are, because in the end that's important. You don't want to be dealing with terabytes. So this is a 80-core machine with 8 NUMA domains. On the left I have the Cholesky benchmark. On the right I have, remember I kept saying scientific applications, that's the very important recursive Fibonacci, right? We get to have fun sometimes too, as long as we also use the real benchmarks. And essentially what we're showing on the y-axis is the total space in terms of kilobytes for various configurations of the input on the x-axis, right? In the end, what we see here is that the red one is if you just enumerated every task, that's just going to be too big. Note that the y-axis is log scale.
So what are you tracing actually?
So we are tracing essentially the steal operations. That's the key here. And we have a specification of how do you reconstruct the trace from a steal operation. And so we say this is what we store at every steal, and that's how we are able to constrain the space. So we are at about 10 megabytes is the largest, right? So at about 80 cores. On the right hand side for Fibonacci, it's even less than that, less than a megabyte ballpark. Now that was shared memory. So here this is a distributed memory on up to 32,000 cores. On the y-axis, note that this is different. This is kilobytes per core, right? We did this so that you can see the trends better. There are some quite different trends. We have Hartree-Fock, SCF, TCE, and then PG is a genome assembly benchmark, right? These are all genome assembly applications. So these are all distributed memory applications. And our algorithm actually works for 2 different types of schedulers, a help first and a work first type of work stream scheduler. And essentially what we see here is that the worst case here at 32,000 cores is 3 kilobytes per core. Together 100 megabytes. You could do this big computation on a parallel machine, collect it on your laptop and do this analysis, right? Still small. And you could continue scaling even up to 100,000 cores, and I think it'd still be small enough to analyze on a laptop. So that's the key goal that we were going for. So that is the space. In terms of time, this is on the shared memory machine with 120 threads. Essentially, what we see is that one, well, there is lots of variation. That's what work stealing gives us, right? So there is going to be lots of variation. The line around 1, that's the execution with no tracing. What we see here is that independent of the number of threads, we are within a margin of error of just the normal execution. So the tracing does not add any material overheads to the computation itself. And more or less the same happens on distributed memory. There's something funny going on with the AQ-HF benchmark there, that with tracing we are actually faster. I think it's because of something changing the machine between the things that we did in the experiments, say the nodes that we got are different, and that's what gave us this improvement. And note that this is student t-test with 95% confidence, so we are getting statistically significant speed up, which in reality shouldn't happen. Yeah. Now, okay, we've traced it. Let's look at a few things that we can do with it, right? And we'll just take a quick look at it. One, well, we just replay it. Now what we're doing with the replay is that we do a few forms of replay. One, we completely turn off work stealing, where you say, well, you know this is the trace, this is what was executed, just exactly replay it. We call it strict ordered work stealing, the OWS. The other one, we say every process node knows what it needs to execute, but if at any point it's waiting for something to happen but something else gets triggered, some other segment gets triggered, it can execute that. We call it unordered work stealing. It's still strict, there's no stealing going on, but it's unordered. The last one is relaxed, where the idea is that I use the steals from the previous phase, my tracing, as just a guideline. I'll start with it, but then if I run out of work, I'll continue stealing, right? And here what we are seeing is on the y-axis is the time overhead that we get, one being no tracing, no work stealing, any of that. And essentially we see, again, tracing is within the margin of error. Most others don't give us any overhead more than 10%, right? That's the key here. And relaxed work stealing gives us the most overhead, mainly because the work stealing machinery is still on, and we have to split and graft segments of the steal tree that we did the previous iteration, and that has some overhead. But relaxed work stealing gives us something, right? And let's see what it does. I'll show you a few forms of adaptability. So one, let's say that you're doing fib of 48, and these are all normalized, these are times in seconds, right? So that's the first bar, takes about a second. And I'm going to do the same fib of 48, traced it, I'm going to rerun it, but now one of 80 workers is slowed down. And essentially what happens is if you're doing just ordered work stealing, you're going to be significantly slower. But with relaxed work stealing, because the work stealing machinery is still on, we can load balance around it and still get good performance. So this is an important thing because we don't want to say, give me an SPMD program and forget it. We want to still keep the benefits of work stealing and dynamic load balancing in that it can work around noise or challenges in the execution environment, but not pay the cost of just doing work stealing every time, right? So this is another example. I'm going to take a trace on, let's say, P minus 10 processes here, right? And then I'm going to run it on P processes. So here what I did was, well, I ran a computation on 10 processes at some point, I have a trace for it, can I use that to seed on 20 processes? And this is really important because on a HPC machine, it's easy for you to get hundreds or even 1,000 cores, right? It's cheap for you to get a quick job. You could do a quick job on a small problem, get a trace, and then use that as your initial computation seeding, your parallelization on a big job, right? And that way you've done the hard work on the small job, but then you're using it on the big one. Essentially what we see here is that doing that more or less leads to no overheads, right? So this one is if you did work stealing, no tracing or anything on P processes, this is you start with essentially the wrong schedule on a different number of processes and you do relaxed work stealing to basically recover that. Now, that was changing the number of processes. You could change the problem size itself. So here what we're doing is we take a schedule for fib of 48 and then run it on fib of 54, right? So now we're trying to see if I can reuse across problem sizes, and fib of 48 is much cheaper than fib of 54, right? And essentially what we see here is that one is just running fib of 54. This is going to be, so this is the whole fib of 48, right? And this is fib of 54, where we are doing relaxed work stealing here, and you see that pretty much it's able to recover it. So you could trace a small problem size and use that to replay on a larger problem size using relaxed work stealing, and you get what you get at the larger problem size. Okay, so now we've done replay. You could do visualization, and this is again something that's expensive in terms of tracing that happens in many tools. For us, this trace is less than 100 kilobytes, right? So this is something we did on distributed memory machines to, it's sort of a relaxed work stealing. I'll quickly jump to the results. If you see here, so this is on about 128,000 cores. This is, I think, when this was done, pretty much the full machine in Berkeley. Y-axis is the parallel efficiency, and this is basically an iterative computation, and we exploit that fact and then use the steals and the traces from one iteration to see the next. And then essentially what we see here is that as we, this is the first iteration, you see how bad it is, right? And then as we evolve, so by the 14th iteration, we are at about 80% parallel efficiency, right? So you can keep increasing it. Now the important thing here is that, so this line shows us amount of work in terms of number of tasks per core, and this number is actually pretty small. If you see here, so this is 100, so this is on average 100 or less, right? Little less than 100. Typically work stealing is fine as long as you have enough work, and they define enough as much more than the number of cores, right? This is actually pushing the limit, right? So we are doing really small computation and still we are able to scale by exploiting this property.
So what you're optimizing is the fact work stealing has a malware where I'm trying to steal from that node and that node has no jobs, then I have to go to somebody else and so on. So that is what you're optimizing.
Yes. So that's one aspect of it. Now let's quickly jump to data locality optimization. Right? It does a few different things for us, right? It can help handle load imbalance. That's the whole line of work we talked about. There's also data locality optimization you could do. So if you write this code, for example, in OpenMP, 2 loops, what will happen is that you get array A nicely partitioned, array B nicely partitioned. The thread 1 would access data on its local memory, right, or its NUMA domain to access it, get really good performance. So on 80 cores, you get about 169 milliseconds for this computation. Do the same thing with Silk. The problem is that these two phases have nothing to do with each other, right? So this is your allocation, and this is how the threads are going to access it, and the performance is now easily 3x slower. So now we have a machinery to trace. Can we use that to actually improve data locality? So what we do is we capture the steal tree and see if it's load balanced. If not, migrate the data to be local for this particular steal tree, do relaxed work stealing again, and then see if it's load balanced. And you keep doing this. So you migrate the data and you adapt the computation. And once it's load balanced, you turn off work stealing, you do strict ordered replay, but you still measure to see if you see a load balance. If you do, you go back to doing relaxed work stealing, right? So this is a way by which we can actually improve data locality. And in the interest of time, I'll skip results which show that it mixes the best of both worlds. You can get the benefits of OpenMP static partitioning, and when OpenMP fails in cases where two phases are doing differently, this approach still gives you better performance, right? And in all cases, it's much better than Silk. So I'll pretty much stop here. The idea is that we want to adapt work stealing for the locality of our schedules and for cases where the user can also give us information, right? So I didn't talk about user specification or control of the partitioning or the steal tree. The user can also give us information. We want to take that information and then try to incorporate it still into the overall work stealing framework. We don't want to completely throw away work stealing or completely get the user out of the loop. We want to combine both to come up with a better schedule. And with that, I'll stop.
So this is predominantly on very regular data access patterns, right? So if my data access patterns are dynamic, then yeah, but most of your applications are probably of the former sort.
Yes, either they are pretty much the same, you're doing a convergence calculation like a sparse matrix vector multiply, or they slowly evolve. The classic example they give is think about a cyclone evolving in a geographic grid. Right? It's going to go slowly.
So are people using this? I mean, are you guys using this within some of the larger applications?
That's part of what we're trying to do now. So now we are trying to incorporate all of these into TAM as the underlying runtime for the tensor algebra methods.
So have you thought, particularly when you go think about the polyhedral, or the polyhedral model, have you guys thought about doing kind of linear algebra-like optimizations on your tensor algebra, right? I mean, if I write in an abstract specification of whatever it is that my chemistry problem has me do, there might be some very obvious things, like, from the linear algebra standpoint, not necessarily the polyhedral standpoint. And I'm curious, what's the relationship between those two? So here's a very concrete example. Maybe I'm multiplying 3 matrices together, and there's a very specific order in which I do the associativity. I get a very big win because of the dimensions, right? Is that something that the polyhedral model would actually be able to solve, or is that about, like, future work?
It's being done right now, but it's being done above the polyhedral model.
I see.
So essentially, especially for example, in the chemistry context, there is a whole line of work from specification of the problem down into getting into individual tensor algebra methods, right? And specifically at that methods, we are now working at a layer where we are assuming we are at the form C equals A times B, while in reality, we get the change that you mentioned.
Yeah.
And there is a separate optimization framework that's going to factorize that. And it gets more interesting because it's not just that the order matters, but then there's also symmetry involved in some of these spaces. And you want to preserve the symmetry. And in some cases, even specification of these symmetries is complicated. So we are working with the chemist to have that done. Then we have an automated tool to factorize it, then do common sub-expression elimination at that level. Then we get down into the tensor algebra level.
I would submit that it gets even more complicated than that. You can trade-off representation versus convergence rates and have an even more global optimization space.
Yeah.
Great.
Any more
Thanks.
questions? Thanks, Peter, again.
Yeah, thank you.